it's time to start with our section number 1 from chapter 5, which is the batch reactor data analysis. We do this for rate analysis. Now, the batch reactor is typically homogeneous, and that means that we either work with liquids or gases. So the reactants are liquids and the products are liquids, or they are gases and they finish as gases. We are collecting data essentially for concentration. We want to know the concentration of a reactant. Maybe pressure, because then we can relate to partial pressure. Volume of the tank, maybe, if it's changing, which will not be the case, but you may use it. And the most important one is time. You know that batch implies the accumulation term, which is the change of moles with respect of time. So you don't measure this, which is either concentration by pressure or volume, because then you can relate to concentration, of course. You will not be able to pair those datas with time. And you don't have these, well, your data is useless. So be sure always to make the experiments with both type of data, either concentration and time. Now let me show you the general methodology for a batch reactor. The first thing we're going to use or to say is the rate law, which we're going to postulate the rate law. We are going to typically do it by power laws in these presentations or slides, but you can also use this method for special rate laws. For example, Langmuir models and many other models, which are something like these, I remember, and they have something like this, which we are not like power laws, but they do apply, so why not use it? Remember, power laws is essentially K times concentration of A to a n power, and maybe even also B to a other, let's say, beta power. Perfect. Once we say, for example, my rate law will be this one simple, or the one I'm used to, which is a constant here and concentration here. We select the type of reactor. And because we're using, maybe we're going to use it in a batch, or in a CSTR, or even in a PFR, we want to use the batch reactor, which, if you remember, has this form when the volume is constant and no inlet, no outlet. You got the rate here, you pass the volume here, so that's why moles change to concentration, the time, and negative here. Now, once we done that, we need to do the experiment and process the data in terms of measured data. For example, if you use, I don't know, you use some equipment that gives you some numerical data, you need to use that data and convert it to concentration. So if you have, I don't know, partial pressure, you can change it easily to concentration. Try always to work with concentration, or at least moles, because moles, you know that you can change them to concentration depending on the volume, etc. Now, we got our model. We need to simplify as possible, because then it's going to be way easier and it's going to work better for our model. So if we got our reactant in excess, which this is actually one method we're going to see in the next video, we can use it as constant. Why? Because if we got a lot of B, let's say we got A plus B gives you C, and I'm using 1 mole of A and I got, I don't know, maybe 100 moles of B. So at the end I'm going to have 99 because I can only react 1 mole of B. So technically our concentration is constant. 100 to 99 is not that huge difference, so why not choose it as constant? And well, that's what we're going to see in the next video, but that's a small peek on the video. Now you may also say that the initial concentration of A, or this one here, of the reactant is so small that epsilon, which remember epsilon is this delta and y of A0, is so, let's say if you have 0.01, well, that's almost 0, so multiplying something times 0 will be 0, and this epsilon will become 0. So that's the first 4 steps. Now let's go, once we got our model, we already done our experimentation, we got the data, we need to calculate the rate of reaction. as a function of concentration, which will be this here, function of concentration, to determine the reaction order. And then we will need to apply these models, for example, access method, the differential analysis, either using graphical method, numerical method, polynomial fit, whatever method you use, you're using the differential analysis. But this is the use of differential data. Or maybe you want to use the integral method, which is integrate this and graph it and see what fits better. Or even use the initial rates, especially if it's a reversible reaction, it will be useful. Or the half-life method. Whatever method that you choose, be sure it applies, because not all methods are the same and don't apply to all the conditions. So once you apply your method, you are essentially done. You got your method, and you will know later that you will get the order, let's say first order. And not only that, many times you will get also the value of the constant rate of reaction. And in the next video, guys, we're going to see the excess method. So keep watching, because this is the most important part on the section.
What's up, guys? It's me, Chemical Engineering Guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos, or if I should be changing something, or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues, or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. Thank you guys for the support and the love.